Start with just a big thank you to Divya and the rest of the organization panel. I've been super impressed this week with the efficient moderation that's been going on. So thank you for that and for making this happen. So as Divya said, I work on the Libfabric team, and I'm currently focusing on adding device support to the OFI shared memory provider for allowing Intranode device-to-device communication. So we've heard a few presentations over the past week discussing different devices and how we can add support for GPUs or other devices in order to leverage that computational power for HPC workloads. So for OFI, this involves various levels of changes, including generic support to expose for providers, as well as some provider-specific changes, such as what my colleague Jin Sheng presented on Wednesday regarding the DMA buff changes for using device memory with the NIC. Another area for adding the support is specifically in our shared memory provider, which is what I will be presenting on today. So in this presentation, I will be giving an overview of what is involved in GPU support for the shared memory provider, the OFI changes and additions that we have added to expose and facilitate that support with applications and middlewares, the specific shared memory protocols and how we are modifying those in order to provide better device support, and also the generic device-specific operations that we've identified to provide device support across the board for providers to leverage. I'll note right now that this is all work in progress and the specifics are constantly being modified and adjusted. So I will not be providing any performance data, but rather just discussing the goal and the current and planned changes going on, all of which is experimental. So next slide. So when we talk about adding GPU to GPU communication and OFI for the shared memory provider, what we're talking about is modifying the existing shared memory architecture on the left that provides transfers from host memory for execution on the CPU and adding support for various types of GPU and interfaces on the right. So the shared memory provider can hook into these low-level software APIs for different types of GPUs. And for use on the device memory on the GPUs. So for example, if you had an NVIDIA GPU and allocated memory on that NVIDIA device using NVIDIA's CUDA API, the shared memory provider can use CUDA API calls to manage and move memory on that GPU into host memory or another NVIDIA device directly. Similarly, if you had an Intel GPU and allocated memory on that device using the Level 0 ZE API, which Sayantan touched on in the previous presentation, which is the driver API and backend library that exposes access to Intel GPUs, we can use comparable ZE calls to copy the memory as needed into host memory or another device. So this allows the application using OFI to use various different compute devices for their workloads while still being able to use OFI for their communication. Next slide. So in the existing support, when transferring to and from host memory, we have two different ways to copy the memory to another process. We can either go through the shared memory region using bounce buffers, or we can copy directly from the other process. Next slide. This requires using either a simple mem copy into or out of the shared memory region for smaller transfers, which are under 4K, or using a CMA read or write for larger messages. CMA, in case you are not familiar, is a Linux kernel call called cross memory attach, which exposes process memory and allows for memory copies across different processes. Next. So adding GPUs into the mix, we now have to determine what comparable calls to use when copying into and out of the shared host memory from device memory, as well as copying to and from device memory across processes as well. Next. To do this, we have to use the correct memcopy call or sequence of calls from the API that owns the memory, as well as pass the IPC or inter-process communication handle information between the processes in order to access the device memory from outside of the owning process. Next slide. In order to know which call or protocol to use, both the sender and receiver need to know whether the source or target memory location is on the host or a device, and if it's on a device, which device is it on? Next slide. Subsequently, OFI has 4 new API additions to expose and request proper support for transfers involving a GPU. Next. The First change is just a simple capability bit, HMEM, for heterogeneous memory, which the application can use to request a provider support or enable transfers to and from devices. If requested by the application, any providers that have not added GPU support should fail the FI get info call. Next slide. The second change is a new memory registration mode, FIMRHMEM, which specifies that the application should register all device memory and also provide the interfaces with which they were allocated. So this eliminates the need for a provider to query all the devices to determine where the buffers are located. Next. In addition to the request for registration of all device buffers, a few fields are added to include supplemental information to the registration call as well. The first is an interface attribute to specify which interface manages the memory region and also tells the provider which API calls to use when copying to and from the memory buffer. So here we have defined types of interfaces for host memory, FIHMEM system, also for NVIDIA GPUs, FIHMEM CUDA, and Intel GPUs, FIHMEM ZE, telling us which library calls to use for that registered buffer. Next. The other registration attribute added is a device field, indicating on which device the memory is located on for use in systems with multiple devices. So this varies by the interface that we're using. So for example, for CUDA, this is just an int, which is equivalent to the CUDA type CU device. So those are the 4 additions to expose and facilitate the device support between the application and the provider. Next. In order to allow existing applications or middlewares to use GPU memory without changing their OFI calls and implementation, OFI will also add a new hooking provider called HMEM hook, which will hook into any necessary OFI calls such as FI send or FI receive. It'll determine the location of the memory, then cache and register the memory buffer with the proper attributes for use by the provider. So from the application's point of view, it can pass in any memory on any device or the host without having to do any extra registration. From the provider's point of view, everything has gotten registered properly because the hooking provider has done that for the application. However, use of the hooking provider obviously has overhead for all the memory discovery and management. So direct use of the provider, of the core provider that has HMEM support is recommended for optimal performance if the memory location is known and can be carried through the stack into OFI. Next slide. So just a quick overview on the shared memory provider in case you're not familiar, and all its current host memory protocols. The provider allocates one shared memory region per endpoint to handle all incoming transfers. It has 3 pools of resources to manage these communications. The first is a single command queue for peers to post incoming messages or data requests. It also has a response queue for messages that require an acknowledgement from the receiver. So this is for those larger messages doing that CMA copy across the processes. And then finally, a pool of inject buffers, bounce buffers for medium messages, which are 4K. So anything less than 4K can go through that bounce buffer. Next slide. The shared memory provider uses these 3 main protocols for data transfers. The first is an inline protocol for small messages where the payload is saved directly into the operation command. So this is used for messages smaller than roughly 40 bytes. I forget the exact size. An inject protocol for medium-sized messages where the message is saved into one of the target peers host memory bounce buffers, saving the inject buffer offset into the command. And then finally, a rendezvous protocol where the sender saves the virtual addresses of the source IOVs as well as an offset to the response status of the operation into the source peer's response queue. The receiver will then do a CMA read of the source data and update the response status once the operation is complete. So this is used for messages larger than 4K in order to avoid that double mem copy involved in buffering the data into the command or inject buffer. I'll note that there are also two other protocols that can be used with the shared memory provider that aren't shown. These are two alternatives for the large message IOV message protocol in case CMA calls are not available. So this could be due to not having the correct kernel version, or so the CMA call isn't even available, or it could also be due to incorrect permissions, since the CMA call requires ptrace protections turned off. So if CMA is not available for one of those reasons, we can instead use one of these alternate protocols, which involve either segmenting the large message into 4K chunks to fit into multiple inject buffers, or copying the transfer data into a new shared memory region of the size of the transfer, and then sending the shared memory information over to the peer, who will then open the shared memory region and copy it directly from the shared memory. But I'm not going to be discussing those today, since they're just general support in case CMA is missing. Next slide. So now for the three main protocols, if we start to replace the transmit and receive buffers with buffers owned by the device, we need to identify which one of these copies to replace with device-specific calls. So copying the device memory into the host-owned command or inject buffers for the first two protocols requires a device-to-host copies, and then doing the larger device-to-device copies requires some sort of device-specific inter-process transfer. Next. The device host and host device copies can be replaced with similar intra-process device mem copy calls, while the inter-process support can be added by having the peer get an IPC handle for the buffer, sending it to the peer, and having the peer open the IPC handle for use in its device copy. Next. Sorry, next, one more. These additions will work functionally speaking. However, device to host and host device calls tend to be rather expensive. So keeping the memory on the device if possible, or at least within the management scope of the device driver, will be much more performant. Next. I guess you can go probably one more. To help with this, we can add another pool to the shared memory region's resources, a pool of IPC handles that can be used as device bounce buffers, allowing the memory to stay on the device instead of having to move into the host and then back onto the device. Next. So in this modified protocol, instead of issuing a device-to-host mem copy into the host's own shared memory region, the sender can instead use one of the IPC buffer handles to do a device IPC copy into the peer device buffer, and then save the offset for the handle in the command. The receiver can then issue a device mem copy from its own device buffer into either host or device memory. So we're avoiding that extra unnecessary device to host or host to device copy if necessary. Next slide. So in order to implement all of these protocols and modifications, we have outlined a list of device operations that can be defined for any device API or library for usage in any provider. So they include the following categories of operations. The first is initialization and cleanup functions for any device-specific resources. The second is the memory copy functions for copying to and from device memory within the same process. So those are those simple device to host, host to device. The third is a set of IPC handle functions for copying device memory across processes. So this includes the owning process getting the handle, and the peer process opening and closing the handle when copying to or from it, and then when it's done with it. And then finally, a set of allocation and free calls for using those device bounds buffers that I just talked about, or for any other protocols that might improve performance if the memory stayed on the device. So any provider, like the shared memory provider, can simply identify these scenarios when it might need to copy into or out of the device, or allocate device memory, or use IP handles or whatever, and call the appropriate OFI HMEM ops corresponding to the library that manages that memory. Next slide. So as an example, here are two different sets of calls that might be defined in a set of OFI HMEM ops for Intel GPUs using the level 0 ZE API, and also for NVIDIA GPUs using the CUDA API. Note that not all of the needed calls are shown, and they're not the optimal set of calls or anything, just a few sample calls to illustrate the function of the calls. So the Intel Level 0 ZE API might need to initialize its drivers and devices and create the execution command queues and lists for the memory copies in its init ops. Similarly, the CUDA API might need to make sure its device context is initialized with CU init. The level 0 would then call its append memory copy and execute calls for any memory copies, while CUDA will call its CUDA memcopy. For IPC handle functions, each library has its comparable get, open, and close IPC handle functions. And then similarly for the memory allocation and free calls, both libraries have comparable alloc and free functions to use. So the OFI HMEM ops basically allow simple definition of all needed device calls that any provider can then hook into using the registration interface in order to perform the appropriate function. So I guess next slide is just the thank you, but I just want to summarize my presentation. First of all, the API has 4 new additions to facilitate that support between the application and the provider. Those are the capability, the MR mode, the registration interface, and the registration device. There will also be a hooking provider available for existing applications to use device memory without having to make any changes. The shared memory provider can add device support by using these device-specific device to host mem copies and also adding IPC handle exchange. To help with the expensive copies between device and host, the shared memory provider can also add device bounce buffers, which will allow the memory to stay on the device instead of migrating back and forth between the device and host. And then finally, to provide all this functionality that a provider might need when adding device support, we've added a generic OFI HMEM ops struct to outline all those necessary calls that need to be device or interface specific in order to minimize the changes needed for those providers to add device support. And with that, I will take questions.
Thank you, Alexia. I am having a very slow set of audience today, not getting many questions.
I can relate to that. So
It's Friday, long week. Yeah, so no, I don't have any questions for you today, but I would like
okay,
to thank you
awesome.
for your
I'll
time.
just throw out there that this development is constantly being done. We're working on it right now. So if you do want to participate in this development, please take a look at the Libfabric, pull requests or issues and join in. Thank you so much.
Thank you, Alexia.